Morning, everybody. Welcome back to CHM 102 class. Okay, sure others will join us, but just to recap the fact that we haven't looked at the first family of compounds, organic compounds, alkanes, earlier last week. We went on to start looking at the family with a carbon-carbon double bond, known as alkenes. We said some things about their general representation. Also talked about some of the simple uses in manufacture of polyethylene and things like that. We went on to look at the physical properties. Well, first we talked about their nomenclature, generally looking at how they are named, and looking at both the common name slash the IUPAC nomenclature. And that led us to looking at both their physical and later their chemical properties. Under the chemical properties, all the reactions, we looked at the fact that this class of compounds can exhibit addition reactions. And we said under addition reaction, you can have addition of a symmetrical reagent. We looked at hydrogen, we looked at halogens as examples of symmetrical reagents. And then we went on to look at cases where you have addition of an unsymmetrical reagent. And in case of unsymmetrical reagents, what is important really is the case of addition of such unsymmetrical reagents to unsymmetrical alkenes. So where you have, for instance, the case of propene, which is not symmetrical, and we're reacting it with HBr, for example. I went on to say that the addition would normally follow a rule that was propounded by an old Russian scientist by the name Vladimir Markovnikov. Okay, so the Markovnikov addition suggests that the double bond picks up the proton and forms the more stable carbocation. Okay, and in the next step, the halide, or in this case bromide, then adds in. And in wrapping up what we did last week, I said there is an exception to the Markovnikov rule where you have what we call an anti-Markovnikov addition. We said specifically that happens when you have hydrogen bromide, or HBr, bromic acid, in the presence of a peroxide. Okay, there has to be a peroxide, and this only holds true for hydrogen bromide, HBr. All right, so that was how far we were able to go last week. We'll continue with the next reaction, again looking at what is addition, an addition type reaction. In this case, we're going to consider hydration, that is addition of water. Now, ordinarily, water, if you add ordinary water to alkenes, there's no reaction because water itself is weakly acidic. It's too weakly acidic for it to be able to generate the electrophile needed for the reaction. So what we use in the lab is acid, okay, a dilute form of an acid. Okay, so we use an acid which in turn catalyzes the hydration process. It is still addition of water, and remember that a catalyst is just aiding the reaction to go faster. So it's actually water that we're adding, not acid, rather. And so this reaction results in the formation of an alcohol, okay, which it actually follows the Markovnikov rule, and it is regioselective. On the next slide, I'll just show what that looks like. So the acid now the point is we're using so this is H3O plus, okay, indicating that you have, just you've added some drops of acid to catalyze the process. Okay, so you have that acid species, and that easily makes H, okay, available. So the double bond, which is an electron-rich center, okay, remember, it's rich in electron, it has pi and sigma electrons, picks up. So again, always note, we start drawing curly arrows when we are showing the mechanism. Remember, the mechanism is basically how the reaction happens. We're trying to give an illustration of how the reaction happens in a way that shows stepwise what happens first and what happens next. So with the curly arrow, that arrow, okay, you can see that the electron-rich center picks up the proton, and as you can see, the arrow starts from the double bond, okay, and comes to, so the arrowhead is pointing to the hydrogen that is, the acidic hydrogen, all right? So it picks up that proton, and when it does, there will be the formation of a, so the double bond is between carbon 1 and carbon 2 right now. So there will be formation of a new bond between carbon 1 and the hydrogen that is picked up. Okay, I'm just trying to use this so that you can understand or follow what I've put down here a bit better. So when that bond is formed, it means that that the two carbons that carry a double bond have 4 bonds coming to them. Okay, remember the catenation of carbon. But once this one, the double bond picks up that proton, the middle carbon is not going to have 4 bonds coming to it. So it will have a formal charge of +1, meaning that that middle carbon is electron deficient. Okay, and so we represent that with the plus. That's why you are seeing the plus sign there. Okay, the plus sign on that middle structure indicates that that carbon is electron deficient. So what then happens is that water is able to attack at that position. Okay, remember, water with the electron-rich oxygen attacks there, and when that happens, you have, okay, please take note, the first step is the slow step. Now remember, when we say slow, it is relative to the other steps. And for any reaction course, there's normally just one slow step. Okay, you can't have slow somewhere at the beginning and slow somewhere at the end. No, there's only one slow step. And that the reaction we indicate as slow really refers to the slowest of all the reactions. Okay, so really we mean slowest. But so that step happens. You have the formation of the carbocation. Remember, this is a carbocation, and this is a secondary carbocation, if you notice. Okay, the carbon carrying the positive charge is connected to 2 other carbons or connected to 1 hydrogen. So that's a secondary carbocation. So the water attacks that carbon to form this species here, which has a positive charge still, because the oxygen will now have a formal charge of plus. Remember that there are now 3 bonds coming to the oxygen if you look at it carefully. Okay, so what then happens is that water picks up the proton from that new extended structure that has an alcohol moiety, but the alcohol still has an extra hydrogen. So water picks up that proton to regenerate the, okay, when water picks up that proton, it regenerates the catalyst. Remember, the catalyst is H3O plus. Please, apologies. I'm doing the drawing with my finger, so it's not as clean or clear as it should be. So it's H3O plus. All right. So that indicates that you have your acid. Okay, that's the acid species there. It's regenerated when the water picks up that proton back. But the important part for us is that the product, okay, is actually an alcohol. So this step is important, and what we need to clearly remember here is the acid that we use. Okay, we could use either sulfuric acid, hydrochloric acid, or phosphoric acid. We just add a few drops of the acid into the water, and then of course it is reacted with the alkene. Okay, but because the carbocation is generated, at times you can have some form of rearrangement with this type of reactions. And the rearrangement is because carbocations will tend to, tilt towards the degree or the higher position of stability. Remember, we have said before that tertiary carbocations are more stable than secondary carbocations are more stable than primary, and primary carbocations are more stable than the methyl carbocation. All right, so essentially we have preparation of alcohol from that reaction of an alkene with water, a hydration reaction. Okay, going on to the next type of reaction, we have halohydrin formation. Now, when bromine or chlorine, okay, those are the two very reactive halogens, reacts with an alkene, you have the formation of what is called, but this reaction must be carried out in the presence of water. It must be in aqueous solution. Remember, we already looked at reaction of alkenes with halogens when we talked about symmetrical reagents. We talked about bromination or chlorination. Okay, in that case, we're looking at the halogen as a gas, okay, or without water in its free state. But here we're looking at the halogen in the presence of water. Okay, remember, I'm sure you remember bromine water. Okay, so we're talking about when the halogen has been dissolved now in water. And so typically in this kind of reaction, I'll go to the next slide to really illustrate what I'm saying. You have, for instance, in this case, propene reacting with chlorine in water. So the chlorine in water generates HO minus Cl plus. Now, the important thing here is to know that if it is bromine or chlorine, the halide, okay, will generate the positively charged species. Okay, it's like, remember, in water you have H plus and OH minus. Okay, so it's that kind of mindset we're using to wrap around this now. So in this case, it is HO minus and Cl plus for chlorine water. And then what happens is that, again, remember, the double bond will pick the positively charged species first. Okay, and then, but the easiest way to understand this is if you look at the next equation here. I'm trying to show you the order in which the reaction happens. We talked about it when we're looking at halogenation of alkenes. Now, what happens first is that the halogen is polarized. So when the halogen is polarized, what you have is the Br, one part of it becomes positive, the other part becomes negative. Okay. Now, when then you have this three-membered ring generated, okay, with a positive charge. So in the first step, bromine or chlorine reacts with the double bond to give us this three-membered ring, okay, with the halogen in the ring. And then the water then attacks from the opposite side. Remember that in that case, it is the Br minus when we're looking at that, the case of halogenation. It is the Br minus that attacks. But here, because water is available, okay, and it's more nucleophilic, the water tends to attack at that opposite position, giving rise to an anti-addition. Okay, so it follows an anti-addition protocol leading to that as the final product of the reaction. So what you need to remember here is that it actually, if you look at the order, if you look at the product very well, it follows an anti-Markovnikov type addition. What I mean is that the positively charged species does not go, is not first picked up so that we have, in quote, the more stable cation type system, which we have for Markovnikov addition. In this case, it follows an anti-Markovnikov type addition, such that the product you will have, okay, like if you look at the example here, 1-butene, if you look at that reaction, you end up with a case in which the Cl is on carbon 2, okay, and the OH is on carbon 1. All right, so it's important to so that if you, when you are going through the notes, you understand that the first step of the reaction is similar to halogen addition, but the second step, water rather than halide, is the nucleophile opening the halonium ring. Okay, so it was just to read that so you can follow. So if you look at in the simple example in the black box there, you see that what we're showing is that if when you have ordinary bromine, you have an anti-addition with the two bromines adding to give a trans geometry. But when you have bromine water in the second equation, okay, the one here, then what you have is Br and OH adding, but still you still have that and that anti or that trans geometry showing. And similarly, if we are using bromine in methanol, then what you have is that the nucleophile will be the methanol rather than the Br minus to give this third product. Okay, I think we've spent a few minutes. I'll give us the first code for today. First attendance code is Z for zoo, F for farm, A for apple, J for jug, E for element. So ZFAJE. ZFAJE. Yes, thank you. I think at least one person has given the correct code. ZFAJE. Okay, so a couple of us have that correctly. All right. Okay, so that will be the end of our discussion of addition reactions of alkenes. Okay, looking at the formation of halohydrins. Okay, now we then go on to oxidation reaction. Okay, which is another type of reaction that alkenes undergo. Now, alkenes undergo a number of reactions in which the carbon-carbon double bond is oxidized. Now, this normally leads to cleavage of the double bond in some of the cases. So, the first class of oxidation reactions we'll consider is what we call the Syn-dihydroxylation. SYN. Remember, we came across that word earlier, and I told you it means same side addition, same side. Okay, so Syn-dihydroxylation. Now, in this case, what we do is to carry out reaction of an alkene, okay, with, well, two major reagents are used for this particular reaction. It's either osmium tetroxide or potassium permanganate. But in both cases, we have a syn addition and it leads to formation of a 1,2-diol. Okay, and that's why it's called dihydroxylation. So we're adding OH. You know, OH is the hydroxy group, and it's referred to as the dihydroxylation. Okay, so well, osmium tetroxide, though well, it's toxic, volatile, and expensive, is actually widely used. And in simple terms, if you look at the equation on the slide, what really happens is that the osmium tetroxide forms, reacts with the double bond in the presence of pyridine to give us an osmate ester. Okay, once that osmate ester is formed, in the presence of hydrogen peroxide, the osmium tetroxide is more or less cleaved off when the hydrogen peroxide reacts, and what we then have is a glycol, or what we call a 1,2-diol. Okay, we have the formation of a glycol, which is also known as a 1,2-diol. So it's a case in which you have formation of that cyclic ester known as the osmate ester, and then an oxidation occurs in the presence of peroxide to generate the catalyst back. Okay, so we have the 1,2-diol or the glycol together with the osmium tetroxide reproduced. So again, in terms of the use of catalyst, I said this reaction, whether we're using osmium tetroxide or potassium permanganate, well, the product is basically the same. Of course, new methods keep being developed for some of these things. But the important thing here is to mention that for the permanganate, it is a cold alkaline solution, okay, that reacts with the alkene to give the cyclic manganate ester. Okay, similar type of mechanism like the previous one. Okay, in that case was an osmate ester. In this case, a manganate ester. So once you have the manganate ester produced, it is hydrolyzed in basic solution to give a glycol. In this case, the potassium permanganate, if you remember properly, is purple in color. You used it during your first semester practical, CHM 107. Okay. Again, remember, all of these things we're talking about, the reason why we go to the lab to do the work is so that it goes beyond just being theory. Okay, all of what we are doing now is just trying to explain the theories that guide the actual chemical experiments. In reality, the real chemistry is done in the lab, and so you must pay attention to what you're doing in the lab. Make sure you prepare very well. Make sure you read each section of the manual ahead of the experiment you are going for, so that if you've forgotten some terms, you can check them up, you can remind yourself, and then you go into the lab prepared for the actual day's experiment. Okay, so permanganate, for instance, you used in the course of CHM 107, and one of the things you know is that it is purple in color. Okay, now that purple color is lost when you react it with an alkene. Okay, because what happens is that it reacts with the alkene to form a diol, and all you have left is a brown precipitate of manganese 4 oxide. Okay, now this simple test is used actually to test for multiple bond, alkene or alkyne functional group. It's called the Bayes test, and we use it in the lab. Okay, so you will still, for those who, in fact, you're supposed to be doing that experiment to now, testing for alkene or alkyne functionality in CHM 108 lab work that you're doing. Okay, so when you have an alkene, well, or an alkyne, and you add it to a clear, deep purple solution of potassium permanganate, the solution becomes decolorized. I'm sure you've heard of decolorization of permanganate before. All right, so again, the product of this reaction is also a diol, as you can see there. It's similar to the first product we talked about earlier. Okay, so that's Syn-dihydroxylation. We then go on to the second type of oxidation, and this is called epoxidation. Epoxidation, okay? Well, in a general sense, an epoxide is a three-membered cyclic ether. Okay, this is an epoxide, a three-membered cyclic ether where you have oxygen as part of the ring. That's why we call it a cyclic ether. Normally, an ether, you have an alkyl group, oxygen, another alkyl group. Well, in this case, it is cyclic, and so it is alkyl group connected to oxygen connected to another alkyl group, but the two alkyl groups are also connected. Okay, so you have what is called a cyclic ether, and so those are called epoxides. The most common method of making epoxides is to react an alkene with a peroxy acid, what we call a peracid. You know peroxides. You know peroxides are oxides that have an extra, ordinarily if you want to say oxide of hydrogen, it should be H2O, but the peroxide is H2O2. So you have an extra oxygen in the regular oxide, okay? And so on and so forth. There are a lot of examples of that. So peracid also means you have an extra oxygen, okay, in the normal. So our normal carboxylic acid is RCOOH. That's the one we have on the right. But the one on the left is a peracid, okay? And what my peracid is, it has an extra oxygen in that for that formula. So just like you have peroxide, you also have peracids. So if you react an alkene with a peracid, what happens is that the extra oxygen more or less tries to insert itself between the two carbon atoms carrying the double bond. So what then happens is that you have the formation of a three-membered ring where the oxygen is within the ring and the two carbon atoms are also part of that ring. Okay, one of the common peracids that we use in the lab is metachloroperoxybenzoic acid, MCPBA for short. Metachloroperoxybenzoic acid. All right, so in terms of epoxidation, the reaction will happen such that if you treat on the second equation on the slide, the trans still being there. If you treat it with MCPBA, which I said is metachloroperoxybenzoic acid, what happens is that the oxygen just inserts itself, into that space where the double bond is giving us the product on the right. Okay, so the double bond, yes, as it is going, is actually a concerted reaction. In other words, and the electrons just flow simultaneously as it forms the bond on the one hand to the oxygen, the other one is also forming almost immediately. So leaving us with a product like trans still being oxide. Okay, so this is epoxidation, and in simple terms, what you need to remember the most is that you have a peroxy acid or a peracid reacting with an alkene, and you have formation of a three-membered cyclic ether called an epoxide. Now, again, still showing that the epoxide reaction is an important reaction amongst reactions of alkenes. Where you have more substitution, that end will tend to react faster. So if you have, like in this case, okay, can somebody name this compound? Name of the compound. Let me see how much of our nomenclature is still in place. I'm not seeing responses to my question yet. I asked for the name of the underlined compound. Oh, sorry, it's on the slide. Oh, no, sorry. All right. Okay, so there's no need to ask the question again. It's fine. I didn't realize that I actually put the name there. Okay, so 1,2-dimethyl cyclohexa 1,4-diene. If you can't name that, you are not right. You are not correct. If you cannot name this compound left by yourself, there's trouble. Okay, at least from what we have done so far, you should be able to name. Now, maybe the only thing you may not have seen in the previous examples when we talked about nomenclature was cyclic. But remember, the cyclic compounds are for a cyclic alkene is broadly under the family of alkenes. So you should be able to name whether open chain, that is acyclic, or cyclic alkanes or alkenes, at least from what we have done so far. Okay, so this typically is 1,2-dimethyl cyclohexa 1,4-diene. All right, so if you treat that with MCPBA, what happens is that the end where we have more substitution, that is between carbon 1 and 2, that's where the oxygen is going to insert. Okay, between carbon 1 and 2, that's where the oxygen will insert. Okay, and just to mention also that you can have direct hydroxylation of an alkene. Okay, you need to really target this, but it is possible. If you use the per acid, okay, and you react it with an alkene, that it is actually possible. So you know that ordinarily, with the per acid, you should expect an insertion of an oxygen there, okay? But if that is carried out in acidic aqueous solution, okay, what happens is that the epoxide, that is the three-membered cyclic ether that is formed, is hydrolyzed, okay, and a glycol is formed, okay. Remember that what happens during hydrolysis is that you have the as H3O plus available, and then that is able to, because these three-membered rings are highly constrained, if you understand what I mean. So remember that even for alkanes, the bond angle is 109.5 approx degrees. Now, if you now imagine what you have when you have something like a triangle, because the epoxide, as you can see, is like a triangle. So the oxygen carbon-carbon bond, in that oxygen carbon-carbon system, what you have is like they are forced to stay together, because the bond angle is not as much as what you expect for an sp3 hybridized carbon. So it means that epoxides are very reactive. Okay, and as a result of that high reactivity, you can easily have that ring opening. And so what you have in this last example is showing the ease with which that ring can open. And the ring opens to give us a dihydroxy compound. All right, let's pause for a bit and then take the next code. Okay, G for gate. The next code is G for gate, U for umbrella, V for violin, figure 9, and X for X-ray. So that's GUV 9X. GUV 9X. Yes, number of you have that correctly already. GUV9X. Okay. All right, so we'll go back through the lecture. And so, yes, you can have this type of, again, this is just showing that we can form epoxides from alkenes. And then C, the third class of oxidation reaction we'll consider is oxidative cleavage of alkenes. Oxidative cleavage of alkenes. And the first reaction we'll consider under oxidative cleavage is ozonolysis. I'm sure we all know ozone. Okay. Ozone is very important to us. Ozone, in fact, forms a protective layer over our atmosphere, or somewhere in the atmosphere, that helps to ensure that we are not too exposed to the rays from the sun. Okay. When an alkene is treated with ozone, ozone is simply O3, at low temperatures, the double bond breaks to give ketone and aldehydes, and in some cases, it could also give an acid. Okay. So in simple terms, the reaction, okay, as shown on the equation below, on that slide, you have the ozone. This is the ozone here. Okay. And it's a simple type addition reaction. We call them cycloaddition. So it's happening in a cyclic manner. And essentially what happens is that you have the formation of a molozonide. Okay, that molozonide formed from the alkene, which is reacting with ozone, then rearranges. It's a rearrangement of that molozonide to give the ozonide. Okay, again, when the alkene reacts with the ozone, you form a molozonide. The molozonide rearranges to give an ozonide. The ozonide is the one that can then be treated in one of two ways. Either you have what we call a reductive workup. Okay, in the case of a reductive workup, we use zinc in acetic acid. Zinc in acetic acid, or dimethyl sulfide. Zinc in acetic acid or dimethyl sulfide. If you use that, what you will have are carbonyl products. So it's either, when I say carbon, I mean, well, mostly the neutral carbonyl. So it's aldehyde or ketone. Aldehyde or ketone. Alkanone or alkanal. I think some of you are still used to the IUPAC naming. So if you go via the reductive workup, and reductive workup simply means once the ozonide is formed, we treat the reaction mixture with zinc in acetic acid, or we treat it with dimethyl sulfide. If we treat it that way, we will end up with either aldehyde or ketone. Okay. We could also treat the ozonide, okay, with hydrogen peroxide. We treat with hydrogen peroxide. That is referred to as oxidative workup. So I'm saying that there are two ways to go. We treat with either one, but what we use in treating the ozonide will determine the product we will have. If we treat with hydrogen peroxide, we end up with the ketone on one end and carboxylic acid on the other end. Okay, I hope that is clear. So you have two ways of, in quote, finishing up that reaction. Okay, and one will either give you a ketone and an aldehyde, while the other will give you a ketone and a carboxylic acid. So, well, the basic idea is that the aldehyde that is produced in the other case, in this case, gets oxidized to carboxylic acid. I'm sure some of you know that already, that you can oxidize an aldehyde to a carboxylic acid. Okay, so typically, I'm showing an illustration of that procedure. So you have the alkene. Again, please try and name some of these compounds, even as you go through the slides. Just practice, name them. See if you can get the name by yourself. Remember that naming is part of what you are supposed to be, the knowledge you're acquiring at this stage. So 2-methyl-2-hexene, we react that with ozone, like I said, at low temperature, minus 78 degrees Celsius. We call those cryogenic conditions. So we're going low, we're going below sub-zero, we're going to minus 78 degrees Celsius. So it's treated with that as the first reaction condition. And then the second condition is zinc in acetic acid. And that's how we normally write it, zinc/acetic acid. Okay, HOAC is acetic acid. Okay, you remember I said we have groups that will represent. I talked about ME, I talked about ET earlier. AC is also in that category. AC represents acetyl. 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 Okay. So when you see ACOH, all right, HOAC, okay, we are referring to acetic acid. So if you remember, acetic acid is CH3COOH. So the whole of this is acetyl. Okay, please pardon my finger writing. All right, so the whole of the CH3CO is acetyl. Okay, so anytime you see that, please know that it's referring to acetyl. Okay, so zinc in acetic acid, back to the equation we're looking at. And what really happens is this, and I need you to please pay close attention. I'll change my marker color. You know, you can see where the double bond is on the starting material, 2-methyl-2-hexene. And just imagine we bring in a line there to divide that double bond, okay, so that the double bond remains, okay, on both sides. You divide it into two, but you still have a double bond on the left-hand side, on the double bond on the right-hand side. And you insert oxygen and oxygen to both the left-hand side and the right-hand side. You realize that on the left-hand side, okay, you end up with this butanol, sorry, and on the right-hand side, you end up with acetone, or what we call propanone. Okay, please look at that carefully and make sure you follow and you get what I'm saying at this point. That when we are carrying out oxidative cleavage, okay, using reductive workup, that what we actually are doing is we are basically cleaving the double bond and adding oxygen to one side, oxygen to the other. I mean, that's the easiest way I can help you follow this process. Okay, so that at the end of the day, we end up with an aldehyde on one side, okay, and a ketone on the other. Okay, aldehyde on one side, a ketone on the other. I know your responses are a bit delayed, so I'm just trying to be sure we are following. Okay, yes, acetone is propanone. It's just a matter of old name and IUPAC name. All right, so that's how we have. So for any alkene that you are presented with, I remember that alkene can also be cyclic. You know, I keep saying, don't always think open chain alone. Remember, cyclic members are also members of this family. So if I say alkene, whether it's open chain, that is acyclic, or it is in the ring form, alkene is alkene. And the rules or the laws we're talking about will apply. Okay, let's go to the second part of the oxidative cleavage, and that is using permanganate. It's called permanganate cleavage. Remember, the first one was using ozone, what we call ozonolysis. This one is permanganate. Now, we talked about reaction with permanganate earlier. But when we're looking at that example, remember I tried to help you see the conditions under which we're using permanganate. And you see that what we are doing here is a slightly different set of conditions. So here, if a basic solution of potassium permanganate is used to treat an alkene, usually alkene is warm. If the solution is warm, concentrated, or if we use acid instead of base, okay, the reaction will not stop at the diol. Remember, we looked at formation of diol earlier. But if we trick the conditions, either with heat, we ensure that the base is concentrated, not dilute, or we use acid, okay, instead of base, okay, acid catalyzed instead of base catalyzed. Then the reaction will not stop at the diol, rather oxidative cleavage will take place. Okay, and it is important that you, okay, so look at the equation now. The middle, I think I need to erase this, my big. Okay, erase that. So this is the middle structure. There is the starting material. Okay, what I've done is to show with one equation to the left, another equation to the right, what is taking place. So if you look at it using acid conditions, that is acidified KMnO4, okay? Acidified KMnO4, if you treat this alkene with acidified KMnO4, you end up with, again, a cleavage at that double bond, but it's like, in this case, you end up with the oxidized version. So it is the acid and the ketone, okay? Again, remember, this is where the double bond is, okay? So you end up with acid on one side, okay? Ketone on the other side. If you use alkaline KMnO4 in the dilute form or applying heat, you end up with the ketone still and the ester, or the non-protonated version of the carboxylic acid, that is the carboxylate. Okay, now this will be formed if we use KMnO4 in alkaline medium, either as warmed solution or in the concentrated version. So in both cases, what we see is that you actually end up with the ketone and a form of the acid. Okay, and that's what happens when we have permanganate cleavage. All right, so let's go on to, let me give you the third code for this morning. The third code is R for rain, figure 8, G for gate, K for kill, T for time. R8GKT. R8GKT. Okay, that's correct. The slides used in class, I have sent them to the coordinator to give to you. Are you saying you have not received them? Please check with your class reps. I think he said he had this platform with all the class reps. Maybe it's not all of them, but yes, I think I made sure he got hold of that last week. So for those still asking for the slides, please see your class rep or ask your class rep. Okay, so essentially that is the end of our note on alkenes. I need to load us to. All right, so we now move on to the next family of compounds, alkynes. I am not sure if the note on alkynes has been shared, but the coordinator has everything now, so I'm sure if he hasn't, he will share that with you later today. I'll just let him know I've moved on to alkynes. So alkynes are also called acetylenes. And they are unsaturated hydrocarbons, similar to alkenes. In this case, we have a carbon-carbon triple bond somewhere in the structure of the compound. They have general formula CnH2n-2. Maybe I should mention that you should also remember that cyclic alkenes have this formula CnH2n-2, not open chain alkenes, cyclic alkenes. Okay. Now, alkynes have that formula as well, CnH2n-2. So that don't think that, oh, all alkenes, for instance, have all alkenes that are open chain have the general formula CnH2n. But if it's a cyclic alkene, the formula is actually similar. The general formula is similar to that of alkynes. Okay, so yes, these ones have an sp hybridization, and as you know, they are linear in shape. At least where the triple bond is linear. Okay, and yes, they're also widespread in nature. The only thing is that while an alkene will react maybe with one molecule of hydrogen, an alkyne can react with two. So in other words, they are able to carry out or do a bit extra in terms of the number of molecules that they will react with. Okay, so alkyne can be terminal or internal. If they are terminal when the triple bond is at the end, okay, it's at the end of the molecule, so it's terminal. They are internal when obviously the triple bond is not at the end, so it's somewhere in the middle of the chain. So we'll come across a few examples of internal and terminal as we go on. Now, acetylene is used in oxyacetylene flame for welding and cutting of metals. It is also used as starting material in the manufacture of a number of compounds. I'm just trying to mention some of their uses in general. Ethine is also used as starting material in the manufacture of polyvinyl chloride, polyvinyl acetate, and synthetic rubber. Now, in terms of naming, alkynes follow the general rule, some of the things we have talked about earlier for hydrocarbon nomenclature. The main thing is to remember that the ANE at the end of the alkane analog is going to be changed to YNE when you are considering the alkyne analog. The position of the triple bond also has to be indicated, whether it's at position 1, 2, 3, and so on. But the main thing again is to find the longest continuous chain of carbon containing the triple bond, and then we try to name every other thing as a subsequent to that. I will also in the next slide show that you can also use the old name, naming them as derivatives of acetylene. Sorry. Okay, so maybe I should just quickly emphasize that before I go on. So alkynes can be named as substituted acetylene. I'm reading towards the end now. Now, using this common nomenclature, 1-butene, for instance, this is 1-butene, can be named as, so if you ignore, so the acetylene is the C triple bond C. The only thing apart from that acetylene now is the extra, those two other carbons that are there, okay, which is C2H5, and that's ethyl. So it's ethyl acetylene, okay? That's, we are naming 1-butene now. In terms of the old name, it would be ethyl acetylene. And then 2-pentyne on the right, okay, 2-pentyne has the acetylene, there's an ethyl group here, there's a methyl group here. So it will be named as ethyl methyl acetylene. Okay, so whether you put the ethyl on the left or you put the methyl on the right, or vice versa, it will still be the same 2-pentyne. Okay, so we could also use those old nomenclature. All right, I think it's best we stop here for today. Let's stop with nomenclature of acetylenes or nomenclature of alkynes, and then tomorrow I will just go on with preparation of alkynes. Again, I hope you are attending the tutorial classes. The tutorial classes are meant to help you in smaller groups. Well, this is not a physical class now, but you're supposed to have a group of maybe 70 or thereabout of you discussing with somebody who puts you through so that you can solve some of the questions. But like I always say, the important thing is that you don't go to any class without practicing those questions yourself. The questions are things that you need to have practiced well ahead, so that if you have problems, the instructor is able to help you in those areas. Okay, so please take your time. Good, you have already, well, most of you already have those tutorial manuals, the booklets. Go through, don't wait till it's time for tutorial before you start saying, where is that my book? Okay, practice it on your own. And if you have questions, when you come for tutorial classes, then you can engage your instructor and make the most of the time. All right, I'll see you tomorrow. Bye for now. Okay, exactly. Okay. So where can I click in case of I want to check?
Yes, sir.
Okay, yeah.
Yes.
Okay.
You just
Okay, okay, okay. Which one? Next class. That would be better. Eh? Thank you very much. Okay. Okay. Yeah. Thank you very much. Good morning, class. I hope you are connected. I hope you can hear me. So, how was your week? Your weekend? I hope all is well with you. By the grace of God, we were able to. We got to where we had a situation with the relationship between we've done this, equipotential, and I gave you some work example in class. And I was about, really what I wanted to do is to give you what you can work with, because I don't like a situation where you will not be able to practice some of these questions. I was about giving those questions when the light went off. So I will probably give before the end of this class. I will let you know those questions I would like you to practice on your own. Though I will give the answer and then you can work towards that answer. So today we want to move on to capacitance. And we said, at least I introduced to this capacitance, and I said it's just a device that store electric charge. You discover that most of your appliances somehow they kind of delay. When an appliance is not yet fully charged, the function of the capacitor is to if it is not fully charged, the energy has not yet been stored, then you can have this kind of that device that stores the charge. Is that what we call? And I was trying to explain that it has two plates, two equal plates. They are equal. Unlike battery, battery, when you talk of battery, you have one long plate and then this smaller plate. The long plate we call positive charge, just as indicated in this diagram. But a capacitor, when you talk of a capacitor, the capacitor is just a device, but the material itself is what you call the capacitor. So when you have a capacitor, you have two equal plates separated by dielectric. I mentioned dielectric. Dielectric is like what we call insulator. It's insulator. And until a capacitor is charged, fully charged, there can be connection. Take, for example, this circuit will not connect. That is, the current will not flow in this circuit unless you fully charge C. And how do you charge C? Is the way we have connected like this. Once you have connected, after sometimes it is charged, then it will stop the charge, and then the electric circuit can complete, can fully, you can take your reading. But if it is not fully charged, it will just look or seems as if the circuit is open. So we said that is what we call the capacitance. And the dielectric is the separation between the two equal plates, the separation. So you can see that in this one,
a potential difference is usually across your battery. And at the same time, you can also connect it across your capacitor. So we can see from here that the capacitance, or when you talk of the capacitor, is directly proportional to the potential difference. That is, the higher the potential difference, the higher the charge in a given capacitor. So that is why you are having Q, that is the charge, equals to the capacitor times the potential difference. We usually use that. So C is equal to Q is equal to CV, where C is we call it constant, but we call it the capacitance of your capacitor. And then your V is your PD across it. And as we said, you have it like that. The unit of a capacitance is coulomb. We call it coulomb. And coulomb per volt, because you said this Q all over V. So because of that, you can Q all over V. As a result, you now have coulomb. The unit of charge is coulomb, and the unit of potential difference is volts. So you can see from here, the unit of capacitance is usually farad. We call it farad, and it is usually with capital F. When they say 10 Fahrenheit or farad, when they say 10 Fahrenheit, you know, it's a very large unit. It's a very large unit. But you can also have what you call microfarad, and that is the symbol of it. You can have nano farad, and you can have pico. You know, nano is 10 raised to power minus 9, and pico is 10 raised to minus 12. So it can be as small as that. The charge on a given capacitance can be as low as pico. So there are two types that we are going to talk here. We have what we call the parallel plates, and we also have the cylindrical capacitance. So the first one that we are going to look at is what we call the parallel plate capacitor. This one consists of two equal plates. Each of the plates are charged differently. Take, for example, we have one charge positive and the other one negative. And you can see the direction. The electric field is usually in that direction. And then the separation between the plates is represented by D. D is just the distance. But don't forget, these are filled with what we call the dielectric. And you can measure the current, and as well as you can measure the volts across a capacitor. And that's why you can plot your Ohm's law, and then you can now find the area. When we want to find the area, we calculate the energy stored in the capacitor. But that notwithstanding, we can say, if we are saying is the charge per potential difference, so we can estimate it. Don't forget, what we have here, this is frequency. You know what charge is. If you can remember, we have a charge can also be related to the quantity of electricity that flow in a given circuit. And that quantity is represented by IT. You can say Q is equal to IT. When we get there, we will talk about it. And since time is involved, then that F that you saw is what we call frequency. You know, time is related to frequency. And you know, the 2 pi F, omega is equal to 2 pi F. From there, you can get your in terms of the frequency. So the second one, as I've said, is cylindrical capacitor. We call it consists of two we call it concurrent cylindrical circuit. Why? Because you have the inner circumference and then the outer circumference. Don't forget, the outer is usually charged with negative. That is the plate. Please, this one is long. We call it cylindrical. This is not cylindrical. You know, when you now draw it in such a like a pipe, you know, the open end is usually, we have just open end is the one we have just bring out. But if you extend it like a pipe, that's what we call it. But this is where what we need. That's why I didn't bring it out. If you make it a cylindrical form, that is like a pipe, your pipe, then you will see this, the inner circle and then the outer circle. And you can see that the inner one is charged positive, the outer one is charged negative. The electric field, that's why the one I represented by E, and then the one that is here, that the inside, you know, each of them will have a radius. If I called the inner one, let's say the inner one, I call it RB, small radius, and I call the outer one RA. You know, RA will be larger than RB. Or if I reverse it, you just know that the outer one is larger than. I can estimate the electric field. Don't forget, our electric field is still between the two charge that we have up here. The electric field, this electric field is still the same thing as V all over D. If you can, from what we know, if you connect a PD across, the electric field will just be V, the potential difference, all over the distance between the plates. The same thing apply here. So, but here we mention what we call electric flux, because there will be a kind of interference in between the charge here and that of the inner cylindrical. So you have what we call the electric flux. So the electric field will just be electric flux all over the area. A is the area. And don't forget, I can represent the electric flux. Is this the same, the quantity of electricity all over that electric? And that is why we have our electric field to be equal to Q all over epsilon times area. Don't forget, you can still represent by what we call this electric field intensity. That is our mu. That one is electric field intensity, and that is, we call it surface charge density. So, and our surface charge density is same thing as Q all over A. Don't forget, when you say density, it can be in terms of area divided by area, or it can be divided by volume. But in this one, since we are saying surface, that's why we have divided by A. So we are saying electric charge density or surface charge density is given by Q all over A. And if you put that one, that's why you are having the epsilon all over the dielectric, which is permittivity of the material. So by the time you equate it, you have this, and then I can calculate the what do you call it? The capacitor, or the capacitor of your capacitance, and that is what you will have. Capacitance here, in terms of dielectric, in terms of area, in terms of the distance, the separation, then is given by that expression. C is equal to epsilon divided by times A divided by D. So you can calculate. Take for example, if I'm giving the permittivity of a material, and I know the cross-sectional area, and I know the separation, then I can calculate the capacitor, the capacitance in that capacitor. So, and that is how to get it. So from here, we can move on to the arrangement. You know, you can have more than a capacitor in a given circuit. Take for example, like this one, I just have 3. And I said, if I arrange 3 capacitors in series, we know that when they are in series, they will have the same charge. The quantity of charge will still be represented by Q. But don't forget, each one is connected across a potential difference. So, and that is why we've gotten this. So if I have 3 capacitors there, then there will be V1 across the charge, C1, and there will be V2 across C2, and there will be V3 across V3. So if I have this, I can calculate the capacitance in a given circuit. Though don't forget, the total voltage potential difference in this circuit, it will just be equal to V1 plus V2 plus V3. V is equal to V1 plus, if I connect the total circuit across it. Please, before we move on, I want to give you this code, the attendance code. I want you to write it now, the attendance code I'm giving you now. I want you to write it down. M, capital M, W, E, 2B. Don't forget, everything is capital except the number that is there. I said M, W, E, 2B. MWE2B. I want you to follow it. Just write it down now. The total potential difference. Look at what I've just from this note. I said the total potential difference apply across the capacitor V is given by the sum of each of what you have there. Each capacitor is in series combination, have the same charge. So that's why you don't see I didn't put Q1, Q2, Q3. It's just Q. Their charge across them are the same. And the total potential difference V is equal to the sum of the potential difference V1 plus V2 plus V3. So, and that is what you have here. So I can get my V1, I can get my V2, I can get my V3 in terms of my Q1. Please don't forget Q1, Q2, Q3 are the same when we talk of series connection of capacitors. So they are the same. So I can say Q1 is equal to Q2 is equal to Q3 is equal to Q. And that is why what I've written there. So you can finally say that when you are having capacitors connected in series, the equivalent, the reciprocal of the equivalent capacitance is equal to the reciprocal of each, the sum of the reciprocal of each of the capacitor. So that is what we have. So once you have capacitance in series, then what you do is just find the reciprocal to be able to calculate the equivalent capacitance in that given circuit. So for parallel, we are going to look at the parallel. Parallel is just similar to what you have. When instead of series, you are having the capacitors connected in parallel all over, just like you have your normal, the electrical circuit. So your Q will just be take note, their charge will not be the same, unlike the series. You know, the series, we said the charge in C1 is equal to charge in C2 is equal to charge in C3. It is not so for parallel. Each of them has an equivalent to C. Equivalent to C. So the total charge is the sum of each of the charges. Then you should know that because they are parallel, as we know in electricity, the PD across the three will be the same. So you can calculate the equivalent. So whenever you are having the equivalent, is the sum of the capacitance in the capacitor. So and as you have in the electric circuit, that's why you have C is equal to C1 plus C2 plus C3. So whenever you have a parallel circuit, you are having the sum of the capacitors. You sum it up. And that is what you have for parallel circuit. You can see energy store. I use this diagram to indicate what I mentioned something the other time when we were talking about the charge. If you can still remember that I said you can calculate in terms of the current, and then you can get the frequency when I was talking about the frequency. So when you are having the energy stored in the capacitor is equal to the work done. Please take note. Work done in charging the capacitor. That work that you did in charging the capacitor is what determines the energy store. And the energy store is equal to the area of the shaded. And if you look at the shaded, you can see that this is like a triangle. A triangle, area of the shaded. That's the energy store. And what is the area of triangle? Half base times height. So if I have the charge and I have the PD, I will just have base times height, which is V. And that is how we got the energy. I can call it U. That is how we got this one. So the energy stored U is equal to half times the energy stored, which is the work done in charging the capacitance, the capacitor. So from there you get that. And once I get U to be equal to half Q V, don't forget your Q is what? Is the charge. And you know the charge is given by CV. And once you know that the charge is given by CV, substitute there in the first U is equal to half QV. Then you will now have U is equal to half CV squared. Or in terms of Q, if you are not giving V, if the potential difference is not given, then you can also get the Q squared all over 2C. So you can get your C like that, and that will give you that. Then don't forget, I wrote what you have there. Your C is also equal to, that is your capacitor, is equal to in epsilon naught. That is, don't forget, this is permittivity of that material times the area of the shaded as you have it, times the distance between the plates, and you can get your energy. So in terms of your electric field is what we're giving as what you have up there. In terms of your this, don't forget we substituted ED. Don't forget here, since your V is equal to ED, you can put where you have your U is equal to half QV, you can put your ED, and you can also put this C is equal to that. So that is why you are having this equation. It depends on the way, so that you can easily calculate the energy stored in terms of electric field. So in terms of electric field, don't forget this is area times the distance between the plates. And don't forget with this, AD means volume. You can cross-sectional area times D is equal to volume. Don't forget, please, where you saw A squared is not A squared. Cancel it. It is A. A times D is what we give you volume. And hence, the density, the energy density, which is the energy per unit volume. From here, since this AD is equal to V, volume, then you can now divide by V, because AD is equal to V. So divide by V, you will have U all over V is equal to half epsilon E squared. And from there, that is what you have here. And from here, you can estimate your what we call the energy density. You can see that this is a small u. I use small u just to represent the energy density, not the real energy store. The real energy store is capital U. That's the difference. The energy density in an electric field is proportional to the square of the magnitude of your electric field at a given point. And that is what you can see. You can see that U is directly proportional to the square of your electric field. That is very important. And when you say squared, you can see that it's proportional to that of U. So I would like us to work some problem. But before working problem, let me give you the second code so that you will have the second code. Please write the second code. The second code is E8, capital E8, capital B8, U. E8, capital B8, U. E8, B8, and U. Just E8, B8, U. That is the third code. So I will let's try to solve one or two problems before the time, so that at least we will have a very important discussion. I said, write this question down. Are you hearing me? Write this question down. A 1 microfarad, a 1 microfarad and a 2 microfarad capacitors are connected in series across a 1000 volt supply line. A 1 microfarad and a 2 microfarad capacitors are connected in series across a 100 volt supply lines. Find the charge on each capacitor and the voltage across each. Please, these are very important. I want you to just you can draw the circuit just like the one we did, where you have your two capacity. First one microfarad. You can say C1 equals to 1, C2 is equal to, but they are in series. That is the first thing. You know that we said PD across them, just like this one. PD, just instead of 3, you have 2 now. And you have this one like C1 is equal to 1 microfarad, C2 is equal to 1 microfarad. You have to calculate the PD across C1, you have to calculate PD across C2, and the charge stored by each of the capacitor. I told you, for you to be able to get, you must first of all find the equivalent capacitor. And to find the equivalent, what do? You find the reciprocal. 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And that will be 1 over 1 plus 1 over 2. If you do it correctly, it will be 3 over 2. Then the C equivalent will be 1.2. I mean, will be 2 all over 3. 2 all over 3. Because you make it, you reciprocate it. You move it up. And then the 2 will go up and the 3 will come down. And if you do that one, then you can calculate, since you have gotten the equivalent, then you can now find the charge on each. My Q, don't forget we said the charge are the same. Once they are in series, the charge are the same. So you just say Q, which is Q1 is equal to Q2 is equal to Q, will just be equal to, for the Q1 or the first one, I can just say the equivalence times the voltage across them. You know, you have been given the voltage across. So I will just say 2 all over 3 microfarad times the potential difference, 10 raised to power 6. So if you do that one correctly, please, if you do that one correctly, you are going to get 6.6. If you do that one correctly, you get 6.67 times 10 raised to power minus 4. Please, if you do that one correctly, you will get 6.6. That is for the charge, the first charge. 6.6 times 6.67 times 10 raised to power minus 4 coulomb. So you can see now that in the second charge will still be the same. And once it's going to be the same, you still have that. But how do we get your V1? Your V1 will just be equal to Q all over C1. And your V2 will be equal to Q all over C2. Don't forget we said the charges on each of the plates, because they are in series, their charges are the same. And once their charges are the same, I want you to solve that. Q all over C1. If you do it correctly, what will you have? The first one, V1, will be what? 667. That will be the first one. It's 1,000, not 100 though. I saw one person writing 100. It's 1,000 volts. I say across 1,000 volts. So if you do it correctly, the first one will be what? 667 volts. And what will be the second one? The second one will be what? Yes, it's 1,000 volts. So you just multiply. You have Q all over C1. And I've said the other one will be Q all over C2. because their charge are the same. So the first one, Q all over C1, we just give us 667 volts. The other one you just subtract from 1000, and that will be 333. Very good. Note the 333. Yeah, 333. You are right. I could see some of you are getting it. That's okay. 333. Thank you very much. So let's move on. Let me give you the second one, the second problem. The second solution. I want you to write it down now. Write it down. Write this one down. A parallel plate air capacitor. A parallel plate air capacitor. Air, A-I-R, air capacitor is made of 0.2 meters squared. 0.2 meters squared thin plates, tin, T-I-N, tin plates, and 1 centimeter apart, It is connected to a 50-volt battery. It is connected to a 50-volt battery, full stop. What is the charge on each plate? Let me repeat the question very well so that you can get it. I said a parallel plate air capacitor is made of 0.2 meters squared tin plates and 1 centimeter apart. It is connected to a 50-volt battery. What is the charge on each plate? What is the charge on each plate? That is the question. What is the charge? Yeah, you wrote it down. That's very good. So you can calculate. Don't forget, it's asking for the charge. For me to get the charge, there was one we wrote equations. C is equal to epsilon naught A all over D. Can you remember that? Yes, the one we wrote. Epsilon naught C, because we are looking for, you can first of all calculate your C. C is equal to epsilon naught A, that is multiplied by A, all over D. And don't forget, you can get your area. Please, there is something, the dielectric is a constant, for at least for here. For air, I will give you for dielectric, the air is 8.8, I want you to write it down, 8.85 times 10 raised to power minus 12. 8.85 times 10 raised to minus 12. That is dielectric. That's the dielectric for air capacitor. So it's a constant. So if you substitute, you can get your C. And since it's only C that we do not know, we have been given the volt. We know the battery, the PD. So we can get the charge. The charge will just be equal to CV. If you calculate C correctly, that is epsilon naught. Don't forget, I've given you epsilon naught. If you use epsilon naught, which is 8.85 times 10 raised to minus 12, you can get the area. Don't forget, you have been given 0.2 squared, 0.2 meters squared. So what you just do is that 0.2 times 0.2, and that will be 0.04. That will be the area. So if you do this correctly, yes, I could see somebody who got that C. C is 1.77 times 10 raised to power minus 9. This is minus 9, not 10. If you do it correctly, just substitute. Get your C first. Once you get your C, you can get your Q. My C is equal to, if you do your C correctly, your C will just be equal to 3.54 times 10 raised to minus 11 Faraday. No, you are saying 0.2 is 0.2. You said is already area. No, they said square. Square means length and breadth. Length is equal to the breadth. So you have to multiply the length. If they want to make it square, they will have put that meter squared. They say 0.2 meter, then squared. We are saying it's squared. Length and breadth are the same. So please take notes. It's not so it will be 0.2 times 0.2, and that will give us 0.04 meters squared. So if you substitute that one, you get your C, and your C will just be equal to 3.5 times 10, 3.54 times 10 raised to power minus 11. And your Q, which is CV that we don't know, will just be equal to 1.77 times 10 raised to power minus 9 coulomb. So from what I've given you, if I want to rewrite that one, I can say this is the same thing as 1.77 N, that is nano coulomb, small n. I can write small n coulomb. I can write that. Yes. It's the area is 0.2 meters squared. You square it, and then by the time you multiply, you will have that squared. So yes, this one will be 10 raised to minus 11. You are right. Then you can calculate, put the other one there, put the other one, and then you will get your 1.77. Since you have gotten your column, your C, you can get your Q. Your Q, yes, this person is, yes, that's 1.77 times 10 raised to minus 19 coulomb. But I said minus 9, not 19, sorry, minus 9. Yes. So since we know that 10 raised to minus 9 coulomb is same thing as nano, n, small n. So you can put that nano, and that will give us 1.77 n coulomb. The last question I'm going to give you, I will give you. So I want to give you the third code. I want you to write the third code now. Please, are you there? Write the third code. The third code for the attendance is KGHMJ. KGHMJ. Please, KGHMJ. You want my name? My name is Professor Wade. I may introduce my name last Sunday. I mean last Friday. Last Friday, but no problem. Still Professor Wade. So please, that is the code. As I've said, yes, the code for your attendance. The third code is KGHMJ. So KGHMJ. Yeah. So that will be your final code. Just enter it. So the third questions, which I would like you to solve, I will mention it and then I will summarize so that you can get it done. I said, find the charge. Find the charge. I want you to write it down. I want you to write this one down. Find the charge as well as the potential difference across each of the capacitors. Find the charge as well as the potential difference across each of the capacitors, 3 microfarad, 12 microfarad, and 4 microfarad connected in series. 3 microfarad, 12 microfarad, and 4 microfarad connected in series across the potential difference of 16 volts. So you have about 6 answers that you will provide. 6. You have to provide 6 answers. Because you first of all calculate the equivalent. Don't forget that since each, they are connected in series, you can calculate the effective, the equivalent C. Don't forget 1 over C1 plus 1 over C2 plus 1 over 3. Please, the question, you still want the question. I said find the charge as well as the potential difference across each of the capacitors 3 microfarad, 12 microfarad, and 4 microfarad connected in series across the potential difference of 16 volts. Find the charge as well as the potential difference across each capacitors 3 microfarad, 12 microfarad, 4 microfarad across the PD of 60 volts. No, it's 16, 16. It's 16, 16. 16. So to find that, you find 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Then if you do that correctly, your C equivalent will be 1.3 microfarad. If that is your equivalent, what does that mean? Since they are in series, Q1 is equal to Q2 is equal to Q3 is equal to Q3. Q1 is equal to Q2 is equal to Q3 and is equal to Q. So if you do that one correctly, you get 1.7. You get your C to be equal to 1.5 microfarad. Then you just get 1 Q. 1 Q will be for all. And Q will be just what? 1.5 times 10 raised to power minus 6 times 16. That will give us the charge. And that will be 24. If you get that one correctly, it will be 24 coulomb. Very good. I can see 24. No, 24 times 10 raised to power minus 6, which is microcoulomb. Yeah. 24 microcoulomb. You are right. You are very right. Then you can get your V1. Your V1, you can get your V2, you can get your V3. So if you get your V3, your V1 will be 8. Vivo, 8 volts. Yes, you got it. Your V2 will be 2 volts. And what will be your V3? 6 volts. Because everything is 16. And that is all. 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 So please, I said I want to give you some work that I want you to practice. Let me start with the one we did last Friday. Consider, write this one down. Write it down, and then you try to do it on your own. I want you to do it. I want you to do it on your own. Yes, you have access to the notes. Don't worry. You have access to what you call it. The PowerPoint. You will have access to the class secretary, the lecturer in charge will give you. Don't worry about that. Write this question down. I want you to write it down. 1. Consider a point A, capital A. Consider a point A, which is 85 centimeter north. Consider a point A, which is 85 centimeter north of a point charge, which is, I said, consider a point A, which is 85 centimeter north of a point charge, minus 45 times 10 raised to power minus 3 coulomb. consider a point charge, a point A. Consider a point A, which is 85 centimeter north of a point charge minus 45. Minus 45 times 10 raised to minus 3 coulomb. And a point B, which is 60 centimeter west of the charge, which is 60 centimeter west of the charge. Full stop. Determine VB minus VA. If I were you, you can just draw the diagram. Very simple. Draw the diagram, the one towards north, and that is where you have your A, 85. The one towards your west, that is 60. Then you can calculate your electric field, and then you get your, if you do it correctly, VB minus VA is equal to minus 1.98 times 10 raised to power minus 8 volts, if you do it correctly. So I want you to do it. I want you to do it. So if you do, I'm giving you the answer so that you'll be able to do it correctly. When you get that, minus 1.98 times 10 raised to power minus 8 volts. The second one that I also want you to do, a charged oil drop. Write this one down too. A charged oil drop of mass 1.0 times 10 raised to minus 14. A charged oil dropped of mass 1.0 times 10 raised to minus 14 kilogram. Just write kg. Remaining stationary when situated between two parallel metals. Remaining stationary when situated between two parallel metals. 25 millimeter apart. 25 millimeter apart. And a potential difference of 1000 volts is applied to the plates. A potential difference of 1000 volts is applied to the plates. Full stop. Find the charge on the drop. Find the charge on the drop. Let me read the question all together at once. A charged oil drop of mass 1.0 times 10 raised to minus 14 kg remaining stationary when situated between two parallel metal plates 25 millimeter apart, and a PD of 1000 volts is applied to the plates. Find the charge on the drop. That is the question. If you do it correctly, the answer is your charge, Q, is given by 2.5 times 10 raised to power minus 18 coulomb. If you do it correctly, Q is equal to 2.5 times 10 raised to minus 18 coulomb. Please don't forget you are giving mass. Here you must calculate force. And I want you to know that, yes, 2.5 times 10 raised to power minus 18 coulomb. Please, I want you to know that F is equal to mg will be used here. And then you equate it to the force on the charge. I've solved the problem for you. I've solved the problem. So once you substitute in, you can get force because of the charge that you are having, then as I've said, this is same thing as mg. Once you find your mg, equate it to the force on the charge, and then you can get it. So if you do it correctly, it will be 2.5 times 10 raised to power minus 18 coulomb. Thank you very much. I think we don't need to worry ourselves too much on some other questions. For now, I want you to do that, and I want you to come up with a solution with them, with what I've just mentioned. Please don't, I want you to use 9 points. Don't use 9.8. Let's use a primary secondary school G. Let's use 10. I want you to use 10 because I don't want you to be getting all these so many figures. But use 10. If I want you to use 9, I will put it there. In your exam, if I want 10, I will put it there. If I want 9, I will let you know. Is that okay? So have a wonderful day. Thank you very much. So, bye. Okay.